In this video, we're going to talk about the general material balance equation, the one that we've seen hundreds or maybe even thousands of times so far this year. But in this video, we're going to explore it in a different way. So, as you should know by this point, our general material balance equation is just accumulation is equal to the input minus output plus generation minus consumption. Right? So that's just the generic form of the equation. What we're going to do now is we're going to imagine a process. And so let's suppose that we have a process where we want to keep track of the number of moles of some species A. So number of moles of species A that's involved in a reaction in some reactor over some period of time. Okay, so I kind of wrote that deliberately in a vague way. All right, so let's imagine we have this type of process. And so for this type of process, let's start filling in what each of our terms in our general material balance equation are. And so for our accumulation term, the way I'm going to write it now is I'm going to write it as this delta Na, where the Na here is just the moles of A that are in the process, and delta here represents the change, right? So the change of the number of moles in this species over the course of the process. For the input term, I'm going to write it as equal to the rate of A that's entering the process, so Na in dot, and that's going to be multiplied by some period of time, delta t. For the output term, I'm going to say it's equal to the rate of Na that's leaving the process, Na out dot, times some period of time, delta t. For the generation term, that's going to be equal to the amount of A that's being generated in this process, so gen dot, times some period of time. And then similarly, the consumption term is going to be equal to the amount of A that's consumed in the process, this consumption dot, times delta t. Okay? So now I'm going to write the equation, delta Na. And for the right-hand side, you could see that all the terms on the right-hand side are multiplied by this delta t term. And so this period of time, we're saying it's the same for all of these terms. And so what I could do is I could then pull it out from each of the terms. And I could write the right-hand side like this. Plus gen minus consumption dot. And that's all multiplied by delta t. Okay? All right, and so for these rates, even though it kind of looks like they're constants, I want to emphasize here that they're not necessarily constants. These values could be changing over time. All right. But in any case, I pulled out the delta t, and now I'm going to divide both sides by this delta t, so that we have delta Na over delta t is equal to Na in minus Na out dot plus the generation minus the consumption. What I'll do now is I'll then, for this entire equation, take the limit of it. So I just said that, this process was occurring over some period of time. What I'll now say is we're now only going to look at the period of time that's very, very, very short, infinitesimally small. Basically almost zero. And so if we have this sort of delta NA over delta T, and we're saying delta T is, approaching 0, that by definition gives us a derivative. Okay? And so what we have now is that this dNA dt is equal to all the stuff on the right-hand side. Plus gen minus consumption. Okay? And so what we have now is we still have our general material balance equation, but now we have it in the form of a differential equation. And with this form of the differential, or with this form of the material balance equation, what we could do is, if we solve this differential equation, dNA dt, what we could get is an equation that describes the moles in our process, the Na, as a function of time. Equation that describes Na as a function of time. Okay? And to do that, or by doing that, that allows us to track the moles of A throughout the entire process, not just at the beginning and the end. So we could see its entire behavior. Okay? And so with these differential equations, this gives us a lot of, power in order to, and a lot of the ability in order to study our process. And so just by solving it, this gives us a lot of information that we could use. Now the hard part here is solving the differential equation. And so that's what we'll talk about next.